Central question for today is going to be, how do we tell the difference between an exponential growth and I'm just going to abbreviate this time, exponential decay function. All right, so how do we tell the difference between an exponential growth and an exponential decay function? And normally if you guys were here, in person, I just have you group up and work on these for a couple minutes. Let's just do it together here. So we're just going to match the functions here with the graphs over here. It's about using a table of values if necessary. So I want to go ahead and kind of think about how we're going to use a table of values to help us out here. And so really what that comes down to is, right, just kind of making a t-chart. I'll start over here at number 1. I want to think about x values that I can use, or try, and then plug them in and see what it spits back out. Without really maybe knowing anything about this type of function, what should I try? So generally, if you're just trying things, you'd want to try 0, you'd want to try a negative number, you want to try a positive number and just see what happens. So that's where we're just going to start out. We're just going to start with 0 and a negative number and a positive number and see what happens. If they work, they work. If they don't, then we'll try something else. Okay? And so I say, well, what is 2 to the first power? What is 2 to the 0 power? What is 2 to the negative 1 power? Okay. Well, 2 to the first, of course, is 2. And what's 2 to the 0? Yep, 1, Aiden, right, Mason? Okay. And 2 to the negative 1. What do negative exponents do? Not signs. Negative exponents are division, right, Aiden? But they're also, what's the number that? Fractions, yep. 1/2. Right? Negative exponents aren't about signs, they're about fractions. Yeah, so be looking for one of those graphs that would go through those points, right? We saw that negatives worked, we saw positives worked, we saw 0 works, we got answers for all of those, right? So I'm just going to keep using those same 3 x values to get some more y values. So I'm just going to move on to number 2 before I try to go look at the graphs. I'm going to do I want to generate a couple tables and go see if I can find some of the graphs after I have a couple done. So what happens if we use, same 3 numbers, but now we're using f of x equals 3 to the x. So 3 to the 1, 3 to the 0, 3 to the negative 1. What do we get? Again, 3 to the 1 is easy. That's 3. 3 to the 0 should be easy. 1. And negative exponent, so 3 to the negative 1. 1/3, yep. Okay. Fraction. Okay. Let's do one more before we move over. See if we can pick out some graphs. -1, 0, 1, x, 4 to the x. Of course, 4 to the first, 4 to the 0, and 4 to the negative 1, 1/4. Right? So as we look at those tables and see what could we use that's different about them, right? If we're going to pick something out, we got to know what's different about them. Well, if you notice, they all have the same point in them, so that's not helpful. That right there is not helpful. That whenever we plug in 0, we get 1. So that's not something we can use to discern something. And actually, if we go and look at all of the graphs have the point 0, 1 on them. So that is not something that we can use to discern something. Okay? So that's not useful. So where do we look instead? Let's try using these values here, 1, 2, 1, 3, 1, 4. What can I see over here that matches that? Okay, 1, 2. Oh, there's 1, 2. Right, that was the same as number 1. 1, that's definitely not 1, 3 or 1, 4. Next one, 1, 4. Ooh, 1, 4, that was what, number 3? 1, that's definitely not 3. That's definitely not 3. 1, 3. Oh, that was number 2. Okay? So we were able to use that 1 point to figure out which graph it was. Okay? It's something we're going to answer here in a minute, but like, what do you notice already? What's the same about all these graphs that we just picked? What's different about all the graphs we didn't pick? What's the same about all these functions that we just looked at versus what's different about all these functions we've yet to do? Okay? And how's that going to relate to our essential question? Okay? So let's continue that process a little bit. Keep looking at the other functions here. Those x values worked well for me the first time, so I'm going to keep using them. -1, 0, and 1. I'm going to do 1/2 to the x. So 1/2 to the 1, 1/2 to the 0, 1/2 to the -1. So 1/2 to the first. Well, that's 1/2. Anything to the 0 power is 1. Yeah. And then 1/2 to the -1. Well, what happens there? Right? The idea is that exponent is supposed to kind of distribute into there, so we'd end up with 1 to the -1 over 2 to the -1. When we have those two negative exponents like that, what happens? What happens when we have two negative exponents like that? They don't cancel out. And there you go, Mason, they switch. It goes 2 to the first over 1 to the first. And negative exponents want to move, which of course is 2. Look at those y values, 2, 1, and 1/2. Those look familiar. 2, 1, and 1/2. What happened to them? They're going the opposite order. Look how changing that fraction there, or changing that 2 to a fraction, how these are now going in the opposite order. They're the same values, just in the opposite order. Okay? Can we use that to help us? Can we make sense of why there's a connection here between these other graphs, these other functions? X value 3, -1/3 to the x. -1, 0, 1. Anything to the first power is itself. Anything to 0 power is 1. We get 1/3 to the -1, which means 1 to the -1 over 3 to the -1, which is 3 over 1. So what happens when you take a fraction to a negative exponent? Flips the fraction. Right? Especially -1, right? Just flips the fraction, that's all that happens. Okay? So we should be able to do the last one real quick. One-fourth, 1, and then what's that going to give us? Again? 4, right? Okay. So notice how all 3 of those that we just did still have that 0, 1, right? That point that doesn't really help us. And if you look at the points that are left, like especially the ones they've highlighted, these little tiny points here, like I don't really find those all that useful. Like, is that 1/2 or is it 1/3 or is it 1/4? Like, is that 1/2, 1/3, or 1/4? Like, I really don't know. It's hard to tell the difference between some of those. Or maybe that one's the highest. Maybe that one's 1/2. I don't know. They're so tiny. It's hard to tell. So for me, I don't really like using those bottom, the 1, 1/4, the 1, 1/2. I prefer the other ones. Right? It's a lot easier to tell the difference between 3 and 4 and 2. So that's where I'm going to go look. What do I see happening at -1? At -1, I see, oh, there's a 3. That's easy to tell. At -1, I see, ooh, that's 2. That's a lot easier to tell. All right, -1, oh, 4. For me, that's a lot easier to see. That must be 6, this one must be 4, this one must be 5. Okay, using that other point instead. Maybe it's just my old eyes, but okay. So what do we see here, like broad strokes, guys? What's different about these three functions, in the way that those three graphs look? And what's different about these three functions and the way those three graphs look? If we look at the first three graphs we picked, they all go up from left to right. They're all increasing as we go from left to right. If I had to think about a word here that meant increasing, it's hard to imagine that you don't center on growth. So those are all three are growth graphs. So what do growth graphs look like? They all go up from left to right. Well, if those are growth graphs, then these must be growth functions. What's the difference between a growth function and a decay function? All right, look at those decay functions. Okay. So decay, look what decay is. Right? Decay is not about negatives. Decay is about fractions. Right? Growth isn't about being positive, it's about being bigger than 1. That shouldn't be a foreign concept to you guys. We've talked about stretching and compressing. Compressing was not a negative issue, it was a fractional issue. So decay is not a negative issue, it's a fractional issue. I have a fraction of what I had before. Okay? If I have $500 today and then tomorrow I have $300, I have a fraction of what I had before, some percentage of what I had before. Okay? It's not a negative issue, it's a decrease in a ratio. Okay? So growth functions have base values that are bigger than 1. And decay functions have base values that are less than 1 but bigger than 0, not negatives. Decay graphs go down from left to right. Growth graphs go up from left to right. How do we tell the difference? Okay. All right, so this is going to be something that's important here. When we're talking about exponential functions, and then when we go into logarithmic functions, which is the next thing we're going to do, is this number e. Okay? E is a number. It's like pi. We've given this long, infinitely long, never repeating number. It's irrational. That's what irrational means. Never repeating, never ending. Number, a name. Since we don't want to try to say it. So just like pi, we've given it a letter name. Once we get into the application stuff on Thursday and Friday, I'll try to talk to you guys about where e came from, like how we figured out what e was. But this is really what very basic part of it is that if we divide by a bigger and bigger number and then take that to a bigger and bigger power, it gets closer and closer to this number. But it is a natural number. It's a number that occurs in nature. It's not something that we came up with. It's more something that we discovered. Okay, just like pi. Okay, pi is a number that's been discovered. Okay? But, so e is a number. It's not a variable. So it's just something I need you guys to kind of, I certainly by no means expect you guys to remember the value of e. Okay, it's kind of helpful to know that it's about 2.7, maybe 2.72, kind of like pi, 3.14. But really I need you guys to know that it's a number, it's not a variable, and I need you to know where to find it on your calculator. Okay, so get out your calculator. If you have a TI 30 whatever, there should be like an e to the x button kind of over in the leftish area space. In this area, if you have a TI 30 calculator, if you have a TI 83 or 84, you should have 2 spaces on your calculator where there's an e. Okay? So if you have a TI 83 or 84, there's an e here in the second, and then there's a button down here that says ln. Okay, we're going to talk about that button later, but it's the second ln. You should notice it says e to the x. So if I want to take like e to the 5th power, I would hit second natural log, and then I put in a 5, and I can do e to the 5th. Okay, and that would tell me what that is. Okay? That's one way. The other way is on the second and then the divide button. There's just a second divide is just plain old e. I can still take that and raise it to a power if I want, but it is just plain old e. Okay, so there's the e button. So 2 places on there, second natural log or second divide, kind of right next to pi. You do not want that capital E button right there in the middle. You don't want that. That's something completely different. Avoid that. If you're using an app, the one that I use all the time, just up there on the top right, you see that lowercase e and the capital letter E. If you just hit that button once, it just brings up the E. You can do e to the 5th. Okay, you can do e squared. You can just do plain old E. Okay, so there's E. Okay, you need access to that number on your calculator. You need to know where it is. So if you need help finding it on their calculator. That's good. Sophia, Mason, Jubal, Raylan. Cam, you find it? Okay. Yep. It's a number. We are going to be using that number to do stuff. Okay. All right. Just some basic information about parent functions of exponential growth functions. So the parent function for exponential functions is just f of x equals b to the x. Okay. The variable is the exponent. That's what makes it an exponential function. The exponent is what's changing here. Okay. Our b value just needs to be greater than 1. We already talked about that. Okay, it's growth because of that. When b is greater than 1, it's growth. It can't be equal to 1. It has to be greater than 1. And that's what makes it grow. Okay. There are 2 kind of key points for exponential functions. One of them is 0. When you plug in 0, what do you get? Any number the 0 power is 1. Yeah. So 0, 1 is always a point on exponential functions. Okay. The next one is when we plug in 1. Any number to the 1 power is itself, so 1b. Those are your 2 kind of key points for exponential functions. 0, 1, and then 1b, whatever your b value is. If b is 2, then it's 1, 2. If b is 5, it's 1, 5. B is 2.7, it's 1, 2.7. Okay. So 2 kind of key points that are easy to find for exponential functions. The rest require more calculation. Okay. And this next thing is a new word, which you guys are going to need to know. Okay. We're going to be using it. We're going to talk about it while we're doing this stuff. We're going to talk about when we do the next unit, and we'll be talking about them in the next unit. So this word is a new feature of our graph. I don't believe you guys would have heard this word before. But over the next 3 units, we're going to, all the functions that we are talking about, we're going to be using this, what's called an asymptote. Fun word. A little bit tricky to say. Okay. So asymptote. Okay. Asymptote. Asymptote. Okay. For an exponential function, the x-axis is an asymptote. And asymptote is a line that the graph approaches more and more closely. So what we're seeing here, so what it is a dashed line because it's not actually there. You guys can think of this like the axis of symmetry in a parabola, right? We always drew that axis of symmetry there just to help our eyes see that reflection. Okay? This is a line that we draw just to help us see something. Okay? It's not there mathematically. Okay? So there are no actual points there. That's why we do a dashed line. Okay? But that line is the one that the curve approaches and approaches and approaches. Okay? If we look at a really simple function like 2 to the x, I say like, oh, 2 to the 1, that's equal to 2. And I say 2 to the 0, well, that's equal to 1. And then 2 to the negative 1, that's 1/2. And then 2 to the negative 2, that's 1/4. All right, and then 2 to the negative 3 would be 1/8. we see those y values, as I make that x value more and more negative, those y values get smaller, but they'll never get to 0. Even if I took 2 to the negative 1 million, I would still have this tiny, 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 tiny positive number. Okay? So as far as I go left, this value of this will always be greater than 0. It will get closer and closer and closer, but it'll never actually reach it. Okay? So that's this idea that this graph approaches that line, but it'll never reach it. There's never a number that's so negative that now I have a negative y value. That does not exist. Okay? They'll just get so tiny, but they'll always be bigger than 0. So the graph approaches the asymptote more and more closely as we head off to the left. Okay? And as we look at logarithmic functions next unit, and then after the unit after that, rational functions, both of those functions have asymptotes also. So an idea that gets closer and closer to that line but never touches it. Oops. Domain, so that goes left and right forever. So that's all real numbers. So domain for exponentials is pretty easy. This is an always thing. Anytime we talk about an exponential, the domain will always be all real numbers. The range is your lowest to your highest. So the lowest this gets is right above 0. It does not touch 0, so it gets a parenthesis. And then it goes up forever. So it's our infinity. Okay, so no brackets, not like a quadratic where it hit that number, right? And so we put a bracket on it. This is only going to get close to that number, so it's going to get a parenthesis. Okay. The range for an exponential always looks something like that. It's not always that. It's always similar to that. We can mess with this a little bit. Okay. Exponential growth and decay is a very applicable type of math. We talk about banking, like interest rates on savings and stuff like that. So you're looking at growth in money. You're looking at population growth or population decline for cities, for animals. Okay, you're looking at like radioactive decay for radioactive things, like carbon dating. Okay, you can't have negative money. Can't have negative rabbits, can't have negative people, you can't have negative uranium-234. Okay? These things exist in the positive spaces. Okay? So we don't see numbers below 0. Okay? Mathematically, we can flip that graph down, but application-wise, this is the way this is. Okay? Next side of that, just real quickly with decay functions, it's pretty much the same thing. The parent function is the same function, f of x equals b to the x. It's just that now b is between 0 and 1. Okay. So just switching that to a fraction instead of a number bigger than 1. Remember, not all fractions are less than 1. If you have like 5 halves, that's still growth. 2.9 is still growth. Okay? The fractions that are between 0 and 1, those are decay, not negatives. Decay is not from negatives, that's from fractions. Again, the same thing as like vertical compressions. Okay. Decay comes from having a fraction of what you had before, not a negative amount of what you had before. So the graph falls from left to right, has those same two kind of key points. When we plug in 1, we get 0, or sorry, backwards. When we plug in 0, we get 1. When we plug in 1, we get our b value. So if our b value is 1/2, we get 1 1/2. Our b value is 2/7, and we get 1 2/7. Still has that same asymptote. Yeah, that didn't change. Domain is still the same. The range is still the same. Okay. Still bottoms out at 0, goes up forever. Doesn't matter that it's the left side going up because range is about y, and y doesn't care about left and right. Y only cares about up and down. So it still goes up forever, it still gets really close to 0, but not quite. So those things are the same. So there's kind of our info dump. Anything you guys want to talk about before we go and actually talk about how to graph these? You right, June? Good, Tion? Good, Addison? You'll notice that all the stuff we're going to do today is going to be very basic, okay? It's just 2 to the x, e to the x, 1/2 to the x, 0.25 to the x, okay? There's no shifting, stretching, reflecting, any of that stuff going on right now, okay? We're going to head towards that tomorrow. So just real briefly, I just want to show you what that's going to look like. You know, if we set f of x equals a times b to the x minus h plus k, right? But look what, look where a is, and look where h is, and look where k is. None of that stuff changes how it acts ever, right? A does what a does, and h does what h does, and k does what k does. So if we had something like f of x equals 2 times 1/3 to the x plus 5 minus 7, we should be able to talk about what that does really confidently. You should know what the 2 is doing and what the 5 is doing, what the 7 is doing. The graphing is more complex, but you should be able to describe it. Oh, there's a vertical stretch, and oh, that's a shift left because that darn old h is a liar. There's a shift down. Right? You should be able to talk about that. You don't need to worry about the 1/3. It's this and this and this that we're talking about. And if that was a -2, it'd be a reflection and a stretch. Okay, so all that stuff should be very familiar to you guys. It'll be like the 5th time we've talked about it. So you should be pretty happy in talking about this. Again, the actual doing is tricky. We'll talk about how to get through that. But, okay, so that's where we're headed tomorrow. They want us to do 3 things here. Tell whether the graph is exponential growth or decay before we start. Okay, go ahead and graph it, and then the main range. Okay. So how do I look at the function and just straight off the bat know if it's growth or decay? Okay. Just want to look just at the value of the b value, the base of the function. So that's 2. 2 is bigger than 1, so that's growth. Okay. That's the first thing I can do is just label it growth, and then keep in my mind, like, okay, what does growth look like? Oh, growth better do that when I'm done. Right? My graph better look like that when I'm done. Look at the next one real quick. There's my b value, right? 1/2 is between 0 and 1, so that must be decay. Okay, so what's my graph going to look like if it's decay? Well, better go down from left to right when I'm done. Okay, so that's all you have to do for that. Just, it's a growth or decay. Should be really obvious. 0.25, that's less than 1. That's decay. E, what's E about equal to? 2.7, right? E is bigger than 1. E is 2 something. So whatever it is, it's bigger than 1. That's growth. Okay? It's 2.72-ish. Okay? That's all that is for that. Okay? Easy peasy. And then just kind of having an idea. Okay, what's growth look like? Better curve up, better curve up, better curve up. Okay? How do I graph it? Okay, so we're going to start with these 3 basic numbers. You'll notice it's the same 3 numbers in all 3 graphs. When I can, I'm going to use more values just so you guys have the best graphs possible in your notes. When you're doing your homework, just feel free to use just these 3 numbers. Always feel free to get more points if you want more points. But this is a good starting place. If we can use more x's, we'll use more x's. Okay? So we're doing 2 to the first, 2 to the 0, 2 to the negative 1. Okay? But plugging in 1 should be easy because 2 to the first is 2. Plugging in 0 should be easy because 2 to the 0 is 1. Those 2 points should be very easy to find. And it comes down to slowing down your brain a little bit and going, oh, that's not negative 2. Negative exponents make fractions. Okay? So these 2 points here should be the easy ones, and then you slow yourself down a little bit so you don't mess up that. Okay? And then since 2 is a pretty small number, I'm going to go ahead and plug in 2. Like, this is a small number. I'm going to see what else happens when I plug in the next number. 2 squared, of course, is 4. Well, that's plottable. What about the next number? 2 cubed, that's 8. Okay, that's plottable. The next one's 16. I do not believe my graph goes up that high. Okay? So I'm just getting some more points because I can to get the best picture that I can. Okay? So I'm going to go ahead and plot those. Negative 1, 1/2. 1, 0, or 0, 1. 1, 2. 2, 4. So there's our 5 points. We'd calculated out. Don't forget out your good buddy, the asymptote. So what you're going to do with this, so you guys may not want to draw it because it's on top of the axis, so you may not want to do that, which is fine. It's kind of a pain if you don't have a different color, but you need to at least label it. So just like I expected for you guys to do with the axis of symmetry on those graphs of the quadratics, I expect you guys to label your asymptote for these exponential functions. So you're at least labeling it, if not drawing it in. Okay, when we go and do those shifts later, we take that horizontal line and we bump it up 1. It's now here. And then you guys will be able to draw it. Okay? It'll be more obvious when you draw it. You bump it down 2, it'll be down there, and you'll be able to draw it. So I'll expect you to draw it and label it. But if it's on the axis, I'm fine if you don't want to draw on top of your axis, because I just know it doesn't show up very well. Okay? If you have a different color, feel free to do it. Or if you want to do it anyways, feel free to do it. At the very least, you need to label it. I expect to see your asymptotes labeled, if not labeled and drawn. It's a very important feature of this graph that's going to help us draw the graph. Now we have those 5 points. We know where our asymptote is. I've talked to you guys about how to draw this. We had not drawn a graph like this before. As we head off to that left side, remember it's supposed to get closer and closer to that asymptote. It's really hard to do with our little puny human brains. Okay? So rather than that, I'm just going to pick a point kind of off to the left a ways, just really close to that axis. Okay? Nothing special about it, just off to the left a ways, close to the axis. I'm going to kind of run parallel to the axis through that point as I curve towards those points that I plotted. So right here, I'm just kind of running it parallel to the axis because I can't really actually get it closer and closer and closer. Okay? And I start curving through those. I always have to turn my iPad to do this. That was beautiful. Yeah, I've been practicing that all day. So on that left side should be pretty much parallel to the asymptote. That right side should keep like very steeply angling up. It should be a very steep angle because the next one would be at 16 before it hits that next line. It should not go straight up, but it should be very steep. Okay? Over here on that left side, I do not want to see you guys doing this. It should not bell up. It should not bell down. Okay? It should run flat along the asymptote there. It should not touch it. Okay? So just kind of run it parallel there along that and then curve up. This is what exponential graphs look like. Very flat on one side and then a very steep curve on the other side. It's exponential growth. Look how the change is changing. This only went up half a unit here. Then it goes up 1 unit. Then it goes up 2 units. Then it goes up 4 units. The next one's 8. The next one's 16. The next one's 32. The change changes very fast. That's why we talk about exponential growth or exponential decay as being big things. Like say, the population is growing exponentially. The number of COVID cases are growing exponentially. That's a bad thing. Okay? Because that means they're growing very rapidly. Domain range. Domain's easy peasy. Always, always, always. All reals. You can plug in any number you want. You'll always get an answer. That's what it means to have a domain of all real numbers. You'll always get an answer no matter what number you plug in. Range, lowest number you can get is close to 0, and it'll go up forever. As far as what we're doing today, those two things are set. It's not until we do these shifts and stuff like that that this is going to mess around. Yeah, but for today, this should be all easy peasy. Anything you want me to highlight more on the next one as we do it? Thanks, Aiden. You okay, Sam? You all right, Mason? We got a decay graph. We know it should look like this when we're done. It should be just going down from left to right. Okay. So we have 1/2 to the 0, 1/2 to the 1. That should be the easy ones. It's 1/2, it's 1. We already talked about this on the other page, 1/2 to the -1. Now that flips in there, flips everything upside down, so we got 2. Okay. If I keep going to the right, those fractions are going to get smaller and smaller. That's not very helpful. What if I keep going to the left? What if instead I plug in -2? What if I plug in -3? Okay, how does that work? How do I take 1/2 to the -2 power? How do I take 1/2 to the -3 power? Okay, how do we do that math? How do we make sense of that? 1/2 to the -2 is 1 to the -2 over 2 to the -2, which is equal to 2 squared over 1 squared. And flip everything over, which is equal to 4 over 1, which of course is 4. So 1/2 to the -2 is equal to 4. Similar thing with the cube. All right, it's going to flip, so I get 2 cubed over 1 cubed, which is 8 over 1, which is 8. The negative flips it, and then we distribute the 3. It gets me 2 cubed over 1 cubed, which is 8. Notice those values. All right, 1/2, 1, 2, 4, 8. 1/2, 1, 2, 4, 8, right? Just the opposite order. Because look at those bases. Bases have a relationship. 1/2 and 2 are related. So that's why these numbers here are related to these numbers here, just backwards. Okay? If that was 1/2 and 1/3, or like 3 and then 1/2, you wouldn't see that exact same pattern. But we also have our asymptote at y equals 0. And I expect you guys to do that. Okay. 1, 1/2, 0, 1, -1, 2, -2, 4, -3, 5, 6, 8. All right, it really should look like the exact same picture, just curving the other way. So I'm going to start on my right side next to my asymptote and kind of flat along that. Curve up through there. Nice steep curve on the left side. Nice and flat along the asymptote on the right side. There's my decay graph, my decay function. we just found more points because we're doing this together. Okay, we're trying to make our notes as nice as possible. Domain, easy peasy. Ugh. That's what I say. That's okay. And the range, again, today, range should be easy. Tomorrow we'll see you get messed with a little bit. Really kind of the same idea with the next ones, guys, except for we're doing some numbers that I don't really want to mess with too much, like as far as like trying to figure the math out in my head. Like I don't know what e squared is. I don't know what e to the negative 1 is, right? So with these, I really do just want you guys to use your calculator, which is why we talked about where your e button is on your calculator. Okay. I don't expect you to be figuring this out. Of course, e to the 0 you should know the answer to. And then e to the first is e. Again, you know that e is 2.7-ish. Right? But e to the negative 1, I have no idea what that is. Okay, so e to the negative 1, use your calculator real quick. Best we can really do as humans is even close to the first tenth. So I'm just gonna call that 0.4-ish. Okay, I check what e squared is. I think I already had it up here. 7.4. So I'm gonna go ahead and do that one also, just because I can. E cubed is too big. E cubed is 20 something. So I'm gonna do e squared since I can. Just get one more point on my graph. Okay. Asymptote is still 0. Dashed line. Negative 1 was 0.4-ish. 0, 1. 1, 2.7. 5, 6, 7. 7.4 there. There's only 4 points I could fit. What does an exponential function look like? Growth looks flat on that left side. Sharp curve as we head off to the right. Okay. If you look at this, compare these two. E is a bigger number than 2. You should notice that your graph here is steeper than this one. It's growing faster here than this is. It's got a bigger growth value. So the closer this number is, the bigger this number is, the faster it grows. The closer this number is to 0, the faster it will decline. It'll be fast on this side, then be very slow on this side. It'll be very steep drop here, very steep decay here, and then slow over here. But domain range, easy peasy. Okay. And again, just use your calculator here. 0.25 to the negative 1, 0.25 to the 0, which of course is 1, 0.25 to the 1, which of course is 0.25. Now 0.25 to the negative 1 should just be 4. 0.25 is 1/4. 0.25 to the negative 2 would be 16. So we won't be able to do that one. I did that wrong. Can't do that one. Y equals 0. This one's very steep on that left side. Very steep decay. The closer that gets to 0, the steeper that decay is. And then on that right side, it's very flat. It's dropping really fast, 1/4 each time. It's only 1/4 of what it was each time. look at the steepness of that one compared to that one. Much steeper decay. That's closer to 0 than that was. Okay. I want you guys to try that out. Again, I think some of you guys are, sometimes overwhelmed with the idea that, you can't get all your homework done, so you're not going to do any of it.